do. All right, let's see what we got here. Okay, delete columns to make sort part 3. Part 2 was yesterday. Today's hard. You're given an n array of strings, all of the same length. You may choose any deletion indices, and we delete all the characters in those indices for each string. For example, if you have these strings and deletion indices 0, 2, 3, final array after deletions is BEF, BYZ. So deleting 0, 2, and 3 from each of the strings. Deleting A, C, and D. So the remaining thing is BEF. Okay, sure. Suppose we choose a set of deletion indices answer such that after deletions, the final array has every string row in lexicographical order. Every string in order. Return the minimum possible value of answer.length. So the minimum number of deletions to make that true. So here you're deleting 0, 1, 4, deleting 0, 1, and 4. 0, 1, and 4. So you're leaving BC and AZ. Both these remaining strings are in lexicographical order in terms of just the letters within the string. Okay. This thing, you have to delete 4 things, otherwise if you delete just 3 things, then whatever remains is going to be non-lexicographical order. Okay. And here, G, H, I, D, F, A, B, C, you don't need to delete anything because they're all in lexicographical order. Okay, how would I do this? The first example seemed pretty good. So B, A, B, C, A. So if I were to do some sort of min deletion here, there might be 2 if it's just the single string, would be 2 because I could do the B and the final A, leaving A, B, C, that's sorted. But if I delete the first and last, then obviously it doesn't work for this one. If I kept the B, so if I keep the 0 index, then I would be looking at deleting the second, deleting the third, keeping the fourth, and then deleting the fifth. So I could delete 0, 1, no, sorry, I could delete 1, 2, and 4. That would leave BC and BZ. So these were, yeah. Then the number of deletions. Let's go ahead and just quickly check. Yeah, it's a pretty small subset here. So it's going to be, I would expect this to be n squared or higher. Really, I'd expect this to be n cubed or even slower than that. given the size of things. Otherwise, if they could probably push the boundaries of how long these strings are and how many strings there are. B, A, B, C, A. B, A, B, C, A. 1, 0, 1, 2, 0. So it could be 0, 1, 2. It could then B, B, A, Z, B. That would be something like 1, 1, 0, 9, 1. So 0, 1, 2 is 1, 0, 9. So you have 0. You have to do the 0. Could leave maybe. This index can go to this index. No, sorry, this index can go to this index. And then this index. This index goes to this index, and it goes to this index. This index goes to this index, and that index. Or this index, then this index. 1, 1, 1, 1, 1, 1, 1, 1, 9. One, one, one. All the paths, all the paths. You have a starting index. You go to the next index that is equal to, or to the next index whose value is equal to or greater than that. So many paths. So many possible pathings. So if you deal with indices here, so you're doing indexable. So you go from 0 to 2 to 3, 0 to 3, 1 to 2 to 3, 1 to 3, 2 to 3. Yeah, so 0, 0, 2, 3, 0, 3, 1, 2, 3, 1, 3, 2, 3. This can be 0, 1, 4, 0, 1, 3, 0, 1, 4. Could be 1, 3, 1, 4, 2, 4, 2, 3, 2, 4. Interesting. And the longest of these is going to be 2, 3. Looks like 2, 3 is the only one, actually. And I thought there was another one. Wait, I thought there was another one, like 1, 0, 3. Should be a 0, 3 here as well. 0, 1, 3. Yeah, 0, 3 here. Technically there should be a 0, 1. I guess 0, 2 is available here. Interesting. Zero one 01303. There should be 13014. There should be a 04. I don't think it would. There's just too many possibilities to make all the sequences to see if there's a common sequence that's longest. It would likely need to be something faster than that. Something considerably faster than that. We have the longest chain of increasing values from a starting index. From a particular index. Is everything that uses that index going to be a subset of the longest string from that index? Maybe. So if I have starting at 0, the longest increasing sequence from 0 would be 0, 2, 3, and anything that uses 0 will be some sort of sequence based on some subset of that, some subsequence of that. So 0, 2 or 0, 3, 0, 1, 3, 0, 1, 0, 3. 0, 1, 4. Yeah, that's not gonna quite work, is it? 0, 1, 3 and 0, 1, 4. So yeah, from a particular value, there's going to be the next higher value in that sequence. But if it was something like the sequence is, let's say 1, 2, 1, 3, 1, 2, 1, 3, 1. So you could have a sequence that was like 1, 2, 3. But you could also have 1, 1, 1, 1, 1, 3. So the 1, 2, the 2 then is the next thing that's smallest. But if you skip the 2, then there could be something that's smaller than the 2, but still greater than or equal to the 1. Or let's say you had, 1, 1, 2, 5, 1, 3, 1. It's going to be 1, 2, 5, 1, 5, 1, 1, 1, 1, 1, 3, 1, 2, 3. Just a lot of possibilities there. A lot of ways to skin the cat. Oh boy, oh boy. 1, 2, 1. Go from 1 to 2. And go from 2 to 5, 2 to 3. And then you have to compare that with all those possibilities in the different words. B, 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 B. Suppose we choose a set of deletion indices. Seems like a backtracking one, to be honest. So it's like interesting. It's like chaining. It's like chaining. So I think actually, I have an idea. I think the idea would be based on coming up with relationships between rows, between columns. Because a column can chain with another column only if all the letters within that column here being the indices, all the letters at that index is less than or equal to some other later one. And then can I do that? How long would that take to do that? So doing comparison of columns. So for every column, compare it to every other column. Each column comparison is going to take 100 comparisons. So it'd be 100 times n squared, so it'd be n cubed, yeah. So once I have each column compared to every other column, then maybe I have a set or an array of tuples where each tuple is a good kind of link between two columns, where one column could be considered to be smaller than another column. And then you're going to find the longest link of tuples that you can. I wonder if that works. I wonder if I could shortcut that somehow. So you have a list of tuples between one column and the next column, where the first column, all the letters within it are smaller than the second column, all the letters within that. And then try to find the longest set of tuples. I wonder if you can build a graph based on that, maybe. From one index. From one index, you go to the next index. You're trying to find the longest length within that graph. One node goes to another node. 0 goes to 1, 0 goes to 3, 1 goes to 3, 0 goes to 1, 3. Okay, let me try to do it. So let's say I'm going to think about in terms of columns. Columns is the length of each word, of any word. So it's going to be length of the strings at 0. The rows is just the length of the number of strings. Probably can just do this in one statement, rows and columns. This is almost like putting it in matrix form. So it's like stacking up the words on top of each other like this, like B-A-B-C-A on top of B-B-A-Z-B. So columns is column index with the letter index. So I think I'll have a valid, this could be a set in a list, I guess. For every, this will include tuples of good links, basically column 1 and column 2, where all the strings at column 1 is less than any of the strings at column 2, less than or equal to. So for every column in the range of columns, and I'll say here this is bad is false, bad is good is true. And then eventually it'll be set to false here if necessary. For every row in range rows, if it's not in order for this index, then good is false. So if the word at this row, so strings at this row is the word at this row at this column is greater than strings at this row plus 1 at this column, then good is bad, good is false, break. I think this should be obviously rows minus 1 to not go out of bounds. And then I say if this is still good, then oh boy. It's not comparing columns, is it? It's comparing columns to some other column. Okay. Yeah, so this should be for every other column in range call plus 1 to calls. Okay, so for every column and then every other column. Good is true for every row. This is if strings at this row what am I doing? Strings at this row versus strings at this row for these two columns, right? So so I'm dealing with the same row, I'm dealing with the same word. I'm comparing the letters at those two indices. Okay. Column versus other column. So this should be all rows. So if they're not in order, then it's not good. Otherwise, when it's all done and it's all good, then I would say valid is going to append the column with the other column. Is that right? I wonder if I can build the graph right now. I eventually just want to build a graph. Like 0 can go to 1, 0 can go to index 0 can go to index 1, index 0 can go to index 2, index 0 can go to index 3. Yeah, I think I could build this graph right here. So I just want the longest chain in the graph. So I think it's going to be graph is going to be maybe a default dictionary. Of list. I guess it could be a 2D array in that case. A 1D array in that case. Or no, 2D array where the index goes to the list of follow-up. Maybe I should make this, yeah. Ugh. I need to get better at doing the 2D version. So this is going to be equal to list for each in range of the number of rows. No, is it range of the number of rows or range of the number of columns? I think it's columns actually. So index 0 can go to index 2, index 0 can go to index 3. Yeah. I think that's right. And then I think I no longer want the valid. I think I just want the graph. Graph at the column index appends the other column. Okay. Let's go ahead and see what's going on here. Print the graph. See if it crashes, which I expect it will. Doesn't crash. Okay. Okay, I think that might have been what I was hoping for actually. So 0 goes to 3, so that means that index 0 is strictly smaller than index 3. So B is smaller than 1, 2. B is smaller than C, B is smaller than Z. 1 index goes to 3, 4. So A can go to C, A can go to A, B can go to Z, B can go to B. Okay. Index 2 can go to 3, so B can go to C, A can go to Z. And then nothing follows up for C, and nothing follows up for A. So here, there's like a missing, or the index of these subarrays. The index of these array elements are the input, and the output is the other indices that can follow up on. Okay. So now how to find the longest thing here. How to find the longest thing. The longest chain. Let them go something like what can I do? I can go backwards, right? I can go backwards. Huh. So this thing is 1, this thing's 1, index 0, 1, 2, 3, 4, index 4, longest thing is 1, index 3, longest thing is 1, index 2, longest thing is 1. No, longest thing is 2. 1 plus 1, so it's 2. And then 3 or 4. Feels like it should be faster than that. So then it has to see the longest thing of 3, longest thing of 4. And then see that this is going to be 2, so it's going to be 3 here. And then, sorry, no, this is going to be 2, and this is going to be 2 here. 2 here, 2 here. And then this thing will make it 0, 1, 2, 3. It's also 2. A bunch of 2's. So therefore 5 minus 2 is going to be 3. There has to be something faster than that. Can I go forward in time? 3. Cahoots. Longest thing here is 1. Then longest thing here is 2. 2. Longest thing here is 3. One to 2. Goes to 1 or goes to 2. I feel like I'm so close. So close. Zero goes to 0 goes to 1 or 2. 1 goes to 2. 2 goes to nothing. And 0 goes to 1 or 2. 1 goes to 2. Interesting. So I could do something where 0 goes to 0 looks at all its neighbors. Say it can get to its neighbor and itself plus. Say it can get to its neighbor and itself. So it'd be 1 plus it. And then I go to the next neighbor. I think it's the same speed. It's the same speed. Okay, going backwards and forwards, I think it's the same speed. For every start column. I think I need an answer. Every start column in range of the number of columns. I think it needs to start with 0 or 1. I need a matrix, or I need an array of how long it takes to get to a particular column. I think it should all be starting at maybe 0. I'll call this the distance to get to it, 0 times the number of columns. This is going to be steps to reach column, or the highest steps to reach column. So if I see 1, 2, which means 0 goes to 1, 0 goes to 2. And I see my current number of steps to get to it is 1, maybe. Actually, yeah, maybe it should be 1. By default, it can be it can be just itself as the starting number of steps. So for every start column range, yeah, okay. For every, so I'll just say the follows would be the graph for this start column. For everything that follows, for every follow and follows, then the distance to that follow is the max of the distance to that follow versus 1 plus the distance to this current one. So the current distance is distance at the start column. So 1 plus the current distance. Yeah, I think that's right. And then I just return the max. So the maximum, I think I return the number of columns minus the max, which is going to be equal to the number of deletions. Max of the distance. Okay. Is there anything I should test before I try run this? No. Let's try run it. Sweet. Okay. Well, feels like I could have done this. Alright, let's just clean up and see if I can't figure out what I could do better on cleanup. So you have the graph. It's the list of things that. So graph is the index equals the starting column, and the value is going to be the list of following column indices where string at start is strictly less than string at the follow column. So I'll just format this. I wonder if this is too long for it to be formatted correctly. Graph. Graph to contain info or linking columns. And index is the start column value is list of following columns where the string at the start column is less than the string for every string. Okay. Column and range columns for every other column after it. I could call this for every follow column. It's good is going to be the default assumption. Go through all the rows. Compare at the particular columns. If it's not good, then break. If it's fine, then append the column to the other column list. Steps to reach the longest length of steps to reach the current column. For every start column and columns. I think just consistency's sake, this should be every column. And I guess this should be the other columns. The current distance. And then for every other, I guess following in the other columns. I guess for consistency's sake, this should be other column. And this should be other column. The other column's always following. And I think that should still work. Nope. Start column should be call. Okay. I guess that work could be whatever's. So summary here. I'm not sure what this is all about. Simplified the calculation of the longest chain of ascending columns or non-descending columns. With the understanding that the chain is composed of individual columns where every consecutive column needs to be linked. So So string at column 1 is less than string at column 2 for every string in the array. So if you're deleting 0, 2, 3 and you're leaving 1, 4, then 1, 4 can be considered a kind of good linkage. 1 can be followed by 4. Or let's say something like this, BABCA. The good links would be like 0 can be followed by 2, or 0 can be followed by 3. 1 can be followed by 2, 1 can be followed by 3, 1 can be followed by 4. So you're trying to find the longest chain of good links. Find longest chain of good links where each link has 2 column indices. Let's say column 1, column 2, and strings. And for every word in array, string at column 1 is less than or equal to string at column 2. So that was basically this first portion. So 1, find those linkages in column relationships, or of column relationships. Store as either a default dictionary of list or 2D array. Use 2D above, where the key or the index is equal to the column 1 and the value is equal to the list of column 2. And then from there, use a, I'm not sure what you call this, use a kind of long chain, longest chain, or keep a longest chain array where the index equals the ending column, and value at that index is equal to length of chain to this column, to this ending column. Iterate over each column index and extend the chain to all linked columns from there. So basically, if you assume that each column could end up being the single ending column, as if you were to delete all the other columns besides it. So if you delete everything besides the E, then E ends in a chain that is 1. If you delete everything besides D, then D ends in a chain that's 1, so on and so forth. So that's the starting premise. Then if you go through each and then consider extending from this ending point to the other columns that are linked to it, then the distance to the other column is either going to be however long it might already be to end it there, or 1 more than the current. So if you go from this current one, if the current one's like, B, which is 1 length, then you go to maybe the other B, which is adding 1 more to this B, so like BB. So it's going to be 2 stored into this spot, or currently there's already 1, so the maximum 2 and 1, so now you know that you can get to this B with 2 things rather than just starting with this B. Similarly, you can go to BC and say that now BC, S, ending with C, there's a link of 2, or chain of 2. And then once you do BB, once you start with this index can extend to this C and say that now it's going to be 2 plus 1, so it's going to be 3 to get to C rather than just 2 to get to C, so it's like BBC. And then return the max of that, of the longest chain subtracted from the number of columns is equal to the number of deletions, or the minimum number of deletions. Alright, time complexity. This is going to be O of n cubed to iterate over, to compare every row or every column to every other column. That'd be an n squared operation where each comparison needs to compare every word, needs to compare or verify that every word in the array satisfies the less than condition. So that's going to be O of n. So since it's not constant work inside the loop that goes through n squared, then it's going to be O overall, O of n compare column comparisons times O of n row comparisons per column comparison equals O of n cubed, which amazingly enough was what I guessed at the start, given that this is 100 size. Space complexity O of n squared to keep the matrix or default dictionary of good linkages, good link columns. All right, cool beans.